Well, hello, ladies and gentlemen. This is the beginning of chapter 3. So we're moving on from properties of pure substances, chapter 2 in the notes. And we're moving on to chapter 3, which is work and heat interactions. So we're talking about energy transfers to and from a system in the form of work or heat. So we're talking about either adding heat to a system or allowing a system to do work. So we're going to spend the next week or so or several lectures talking about work and heat. Okay? So we're going to start off that discussion by looking at path versus point functions. Path versus point functions. We'll talk a little bit about how they're defined and how the notation is done. Very simply, a point function is a characteristic or a property of a system that depends on the state of the system. So a point function is directly dependent on the state of the system. You can think of pressure, temperature, volume, enthalpy, energy, internal energy. These are all point functions because they depend on the state of the system. Path functions are quantities that are flows. Energy flow, for example. And these quantities depend on the path taken by the system between two states. So a path function depends on the path the system follows over some process, and point functions depend on the state of the system. So to whet your appetite, path functions are work and heat. Work and heat are path functions. So we'll talk a little bit more about that in a moment. So we're going to define path and point functions. We're going to define the notation associated with path and point functions because you're going to be seeing this throughout the course. And then we're going to move on to our first path function, work. Work is a mechanical transfer of energy to or from a system. Either you push on the system or you pull on it, or you apply some sort of electric current and the electrons transfer energy to the system. So a mechanical transfer of energy we're defining as work. Then we're going to talk about one particular kind of work called boundary work. Boundary work is the energy transfer or the work associated with the expansion or contraction of the system. So we'll talk about boundary work, how you calculate it, how you can interpret boundary work on the pressure volume curve. And then if we have time, we'll do an example. If not, we'll save the example for next time. Okay, so let's get started here. So path versus point functions. Path versus point functions. So how are we going to define them here? A point function depends on state of the system. Point functions depend on the state of the system, not how the system got there. Point functions depend on the state of the system, not how the system got there. What do I mean by that? Well, if I have temperature and volume here, so temperature and volume, and the system goes from one state to another. So here's state 1, and I have some temperature T1 and some volume V1. And then I follow some path, and I end up at state 2, okay? I end up at state 2. The change in temperature, for example, delta T, that's the change in temperature right there. Delta T. That delta T is not dependent on the path taken by the system between state 1 and state 2. Delta T, the change in temperature, is not path dependent as the system moves from state 1 to state 2. So clearly, delta T is not path dependent. What does this imply? Temperature T is a point function. Temperature T is a point function. It is not path, its change is not path dependent. Now, in general, we're going to characterize point functions with a generic variable. I'm going to call variable L a point function. Variable L a point function. So if L is a point function, L is a point function. So L is a point function. The differential change or infinitesimal change in L is mathematically represented by dl. So dl, see the d right there, just like in calculus, represents a differential change or the change in L for an infinitesimal process. Infinitesimal process. The change in L over an infinitesimal process is given by dl. dl, okay? So we're talking about an infinitesimal process with a change in L, dl. That's for a point function. If instead you see delta L, which, by the way, equals the integral of dl over some process, this is referring to an overall process. Infinitesimal process, overall process. Okay? So the change in L from state 1 to state 2 is the integral of dl from state 1 to state 2. Okay? Okay, so examples of point functions are, we already have one, temperature. Another one's pressure, volume, internal energy, enthalpy, kinetic energy, potential energy. All these are properties of the system. So properties are all point functions. Entropy is also a property of the system. So you'll see later, entropy is a property of the system. Okay, so properties are point functions. What about path functions? What is a path function? Well, a path function so a path function depends on the path taken by the system over the process. A path function is dependent on the path taken by the system. Okay? So let's say we got some system and I have, I don't know, some property, prop 1, property 1, property 2. It could be temperature and pressure, it could be pressure and volume, it could be internal energy and enthalpy, who knows? But I got 2 properties on the axes here. And the system starts at initial state, state 1, and it goes to state 2 again along some path. I'm going to call this path, oh, I don't know, A. I guess we'll go from A to B. How about not 1 to 2, how about A to B? A to B, so this is AB bar. That's one path I might take from state A to state B. But then there's another path I might take, maybe it's this way. And so this is AB tilde, okay? The path function, and I'm going to characterize the path function by the Greek letter phi, okay? The path function A to B along path AB bar does not necessarily equal the path function from A to B along A to B tilde, okay? The function is path dependent. Examples of this are work and heat. Now, let's play the same game we just played a moment ago. If you see the symbol delta, Greek letter delta, lowercase delta, and then you have some quantity. This could be work, this could be heat. You see a Greek delta here. This means you have a path function and you are referring to an infinitesimal process. Infinitesimal process, we got the delta here. This is lowercase delta. Lowercase delta, lowercase delta, all right? Infinitesimal process involving a path function. If you see simply the symbol, and maybe you're going from state 1 to state 2, no delta, no uppercase delta, no lowercase delta. This is equal to the integral of delta of the path function, and this is referring to a overall process. Overall process. Overall process. So let's review here, make sure we got the notation down. It's just mathematical notation. If we got a point function, then for a differential process, you use a lowercase d times dl. L is the point function to indicate an infinitesimal process. The overall change in L is represented by delta L, and that's the integral of dl for the overall process. So infinitesimal, overall process. You can call this differential if you like, infinitesimal or differential, overall process. And then if you have a path function, instead of having a d for the infinitesimal or differential process, you've got a Greek lowercase delta. And then the overall process, the integral of delta for the path function is equal to phi 1 to 2, okay? Overall process, infinitesimal or differential process. This is just some mathematical notation because we're going to be seeing these deltas in a lot of different places, all right? Okay, so that's notation here. That's notation. Let me see where I am here. Okay. Let's define our first path function. It's not a property of the system. It represents an energy flow. Not a property of the system. It represents energy flow. Our first path function is going to be work. Work. Work, W. And work represents the mechanical transfer of energy. Mechanical transfer of energy. Work, W. Now, at its most basic, work is a force over a distance, at its most basic. Even in electricity, forcing a bunch of charge into a battery or into a capacitor over a voltage difference represents a force over a distance. So even electric work, current times voltage can be represented in terms of work. So how do we define work mathematically? Well, the differential amount of work, so there's our lowercase Greek delta. Work is a path function. Our differential amount or infinitesimal amount of work is equal to a force dotted with some displacement. F dot dx, okay, where dx is some kind of vector displacement, all right? So that's how work is defined. That's how work is defined. Now, there are lots of ways that you can actually describe work with different kinds of units, different sorts of units. So before we go on and actually calculate some works, let me show you the various bases of work. So let's see here. Let me make sure I got my table the way I want it to be. There we go. So basis. Symbol. And then I have units, as I recall, units. SI units and English units. English units, all right? Okay, so first of all, we have a differential process. Differential or infinitesimal. Infinitesimal, or if you like, differential process. The symbol for differential or infinitesimal work, we just discussed it, is delta W. Lowercase Greek letter delta. Not a D, not an uppercase delta, lowercase delta. It's a path function, not a point function, so this is a Greek letter delta, not a lowercase d. What are the units of work? Well, a joule. That's the typical SI unit for work. Okay? So some kind of work. And then for English units, the big one is the BTU, British Thermal Unit. BTU, British Thermal Unit, all right? So that's an infinitesimal or differential process. What about an overall process? Overall process is just the interval of this, adding up all the work over some process. We go from state 1 to state 2. So for an overall process, we just have the work W. The work W. If you look at our previous treatment here, our notation, overall process, so instead of the Greek letter phi, we have W for work. W for work, okay? Work is the path function we're looking at. So the unit of work, again, is a joule. Work is just the integral or the summation of all the infinitesimal work. And again, we have BTU. All right. Now, what are some other bases here? We have also specific work. Specific work. It could be overall, it could be infinitesimal. I guess specific overall, let's just do that. Specific overall. That is the work per unit mass, which is equal to lowercase w. Remember, when we divide a quantity by mass, usually the case goes to a lowercase. So we have w, lowercase w for specific work. That's for an overall process. That would be equal to a joule per kilogram in terms of SI units, and a BTU per pound, or slug, per pound mass, or a slug or something. I guess it could be weight per pound weight, I suppose. Okay, usually that's not done. All right. And then we also have rate based. Rate based. We have work being done over a period of time. So the unit for that is power. The symbol for that is some kind of power, or if you like, W dot. W dot. Dot means derivative. W dot is the little bit or infinitesimal work divided by a change, an infinitesimal change in time. Delta W over dt, the rate in which work is done. That's a power. Energy per unit time, power. And so that would be what? A watt. Which, by the way, is a joule per second. Okay? English, of course, is a horsepower. That's the big one. Horsepower for English units. Okay? Okay, I'm going to take a pause here. Okay, let's continue on by looking at a particular kind of work. There are lots of different kinds of work, but we're going to look at one particular kind today. And that is boundary work. Boundary work. Boundary work. W bound. Boundary work. So let's say we have a system, a gas or something, and this system is in a piston cylinder device. Okay, so here's our piston, and here's our gas. Could be anything. Could be a liquid, could be a solid. Hell, it could be a solid. Could be a two-phase mixture. Who knows? But let's say it's a gas. And this piston, under the influence of the gas, moves upward a certain distance. So we're going to move up a distance dx. So then we end up in a new position right here. So there's the piston, the old position, and then it moves up to a new position. All right? So our gas ends up looking like this now. Okay? So our gas, there we go. Now this gas has a particular pressure, P. And notice this displacement, dx, is actually an infinitesimal displacement. Because it's infinitesimal, the pressure is approximately constant. Okay? So the pressure is approximately constant during this infinitesimal process. Let's calculate the work that the gas does on the piston as the gas expands. Little bit of work, and that's the work done by the boundary of the system changing shape or volume. So the system has now changed shape and volume, and I want to calculate the boundary work associated with that. Well, the definition of work is force dot dx. Okay? Now, the pressure inside of the gas, inside of the piston cylinder device, is exerting a force on the bottom side of the piston. Okay? And what is that force equal to? Well, the piston has some kind of an area. Maybe it's a circular piston or something. Who knows? So this piston has some sort of an area. A piston. So this piston has some kind of area. So the force is equal to a pressure, which is a force per unit area, times the area of the piston. The force is the pressure of the gas times the area of the piston. That's the force on the piston due to the gas. The displacement, of course, dx, okay? And so the force is pointing in that direction, and so is dx, so they dot together, and you get pressure, area piston, dx. Okay, that's the differential or infinitesimal boundary work associated with the gas expanding over this differential or infinitesimal process. Now, this quantity right here, area piston times the displacement of the piston dx, that is the change in volume of the gas. This extra volume in here, that extra volume due to the upward displacement of the piston, is dx times the area of the piston. So this quantity here is d volume or dV. So the differential boundary work is equal to pressure times the change in volume of the system. So differential boundary work is equal to pressure times the change in volume of the system. Put a box around that. That's an important equation. So that is how you calculate, at least for a differential process, boundary work. Now, one other little thing. As the piston moves upward, the gas is doing work on the piston. It's pushing against the piston, and the gas is doing work. It's doing work against the piston. So this quantity here, PdV, is actually work done by the system. So I'm going to write here, note, by system. This work is being done by the system against the piston. If instead we were pressing down on the piston and moving it downwards, our dx would be negative. It would point in the opposite direction of the force, and we would end up with a negative term in here if we were doing work on the system. So this is positive. PdV is positive when the system does work, boundary work. When it expands and it has some pressure, it's doing boundary work. It's losing energy by doing work, okay? Now, let me show you how to eyeball the amount of work a system does over some process. What do I mean by eyeball? I mean graphically. graphically. So let's say we have some system. Could be a piston cylinder device containing a gas. The gas could be the system. Who knows? So let's say we got a piston here with a gas inside. This is my system. My system is the gas. So this is state one. And then we end up with state two, where maybe the piston is moved upwards. So the gas is expanded. So this is state two. All right. Now, if I sketch the process on a pressure volume diagram, sketch the process on a pressure volume diagram, it might look something like this. Maybe this is state one here, and then I go over some path, and I end up at state two. These are the end states. State one, state two. We have a volume V1. I have a volume V2. And of course, I have a pressure P1 and I have a pressure P2. Okay. And then I take this path, as you can see here. What's the work? What's the boundary work over the process from state one to state two? Well, the boundary work, W bound from state one to state two, is the integral of the differential work from state one to state two. And that's equal to the integral of PdV. Pressure times the differential change in volume as I go from V1 to V2. So the boundary work over the process is the integral of PdV. How is that represented on this graph? This is zero pressure. Let's say this is zero right here. That integral, the integral of PdV, is indicated by the area underneath the pressure curve on the PV diagram. So this integral PdV is equal to the area under the curve. Work bound equals integral PdV, the area under the pressure curve. So if somebody gives you the process on a PV diagram, you should be able to qualitatively determine the work. You should be able to qualitatively determine the work. Maybe we should do a few quick examples here. Maybe we should do a few quick examples. Let's say I have a system that goes from state one to state two. I'll show you the path on a PV diagram, and we can determine which one involved more work being done by the system. So here's our system, some mass. We start off at state one. And then we end up at state two. Okay, I have a V1, a P1, a bunch of stuff at state one. And then I have a V2, P2, a bunch of stuff at state two. And I have the following process. PV. Let's see here. This is state one. That's state two. Let's say this is the process. Okay, that's the process 1 to 2. I'll put a bar on top of it. That's process 1 to 2 with a bar. What if I instead, so the work, the boundary work is given by the area under the curve. So this represents boundary work 1 to 2 bar. Okay, that's the boundary work, 1 to 2 bar. What about, let's take a different path. Let's take a different path. State 1, same state. State 2, same state. But instead, we take the following path. Pressure goes to 0. Expands at 0 pressure, and then pressure shoots up to P2. I'm going to call that path 1 to 2 tilde. 1 to 2 tilde. What's the boundary work done by the system along this path? What's the area underneath the PV curve? 0. Work bound, 1 to 2 tilde, 0. Along this process, it's non-zero. It's some positive value. There's positive area underneath the PV curve. Here, no work is being done because pressure goes to 0 during the expansion process. Okay? This is why work is a path function. It depends not on the end state, but on the path taken during the process. Okay? Not just on the end state, it is path dependent as well. If it's path dependent, if work is path dependent, it is a path function. Okay? Now let's do a little example here. Okay, so let's do a little example here. What we have is air in a piston cylinder device. Seen a lot of these so far. So we have air in a piston cylinder device, which starts off at a certain volume, V1. V1 is 0.4 cubic meters. So initially we start off at state 1. So this is state 1, and we are at some volume V1. Temperature 1, V1, and presumably a pressure P1, and this is air. This is our system. Our system is the air and the piston cylinder device. So we start off with a certain volume V1, 0.4 cubic meters, a pressure P1 of 100 kPa, 1 bar, and then we have a temperature T1 of 80 degrees C. So we got temperature, volume, and pressure of the system. That's good. And then we undergo isothermal compression. Isothermal. Isothermal means constant temperature. Isothermal compression to state 2. So we compress the gas down, and we end up at a volume V2 of 0.1 cubic meters. So we go from 0.4 to 0.1 cubic meters. So here is state 2. And now we squeeze down the piston. So here I have our gas, and I have a volume V2 and a temperature T2, all sorts of stuff, okay? Now, during the process, maybe the system is doing some work. Maybe some energy is being transferred out of the system in the form of work. We shall see. So I'm going to put a work 1 to 2 indicating an outflow of work. We shall see if there is an outflow of work. Maybe there's an inflow of work. After all, we're having to do work on the gas to squeeze it down. We'll have to see. So once we squeeze the gas down for an isothermal compression process, then we have an isochoric cooling process. We transfer heat out of the gas, we cool it down, and we do it isochorically. What does isochoric mean? Constant volume. So then heat is being transferred out of the system, let's say. And it's an isochoric process, so the piston doesn't move. Here's our gas, and we end up with a final temperature T3, final volume V3, et cetera, okay? Okay, what are we supposed to find here? We're supposed to find the pressure at state 2 after we do the isothermal compression. And we're also supposed to find the boundary work. The boundary work as we move from state 1 to state 2 and to state 3. We're supposed to find the total boundary work as we go from state 1 to state 2 to state 3, okay? Along the path 1 to 2 to 3. Okay, so that's the plan for today. Assumptions here. I'm going to assume ideal gas behavior is valid. We're going to check this when we're done to make sure that our reduced temperature is always greater than 2 and our reduced pressure is always less than 0.2 during the process. So we'll check that IGB is valid because we're going to be using it to calculate some properties here. I'm also going to assume that the only work being done is boundary work. I could put some wires in here. We'll talk a little bit more about the various kinds of work on the next lecture. But I could put some wires in here and a resistor and pass some current through there, and I could dissipate. I could do work by passing a current through a wire. I could do something like that. Or I could put a little propeller in here, put a little propeller that spins around, and that would be doing work on the system. We'll talk about that a little bit later. Suffice to say, for right now, we're going to focus on calculating the boundary work associated with this process. Okay, boundary work done by the gas. Okay, so how are we going to do this? First of all, I am going to put up a PV diagram. I keep track of how things are going. I'm going to put up a PV diagram to kind of keep track of how things are going. Always a good idea to create a diagram for what you're doing. Whoops. Okay. So analysis. And the first thing I'm going to put down is my PV diagram. PV diagram, okay? So initially I have state 1, and state 1 has a pressure and a volume. So here is V1, and here's P1. So this is state 1, all right? And I have some pressures and a volume, and I have temperature too. All right? Okay, let's get moving here. Let's calculate pressure at state 2. So how do I get pressure at state 2? Well, note that the process 1 to 2 is isothermal compression. Process 1 to 2 is isothermal compression. In other words, T is constant. T is constant. Isothermal means constant or same temperature. Okay, that's good. Now, how can that help me? So the next question to ask is, what quantities or equations involve pressure that maybe we can use? And remember, the ideal gas law is valid. Ideal gas law has pressure in it. Ideal gas law has pressure in it. Let me write the ideal gas law here. So let's see, PV is equal to mRT. Now, let me solve this for temperature. Temperature equals PV over mR. Okay? Now, the process is isothermal. That means T1 is equal to T2. So note, T1 equal to T2 because process 1 to 2 is isothermal. Okay, well, let me take this equation and evaluate it at state 1 and state 2 and set them equal to each other. PV over MR evaluated at state 1 is equal to T1. So I'm just evaluating the ideal gas equation solved for T at state 1. But this is also, T1 is also equal to T2, which is PV over MR evaluated at state 2. Okay? So this means PV1 over MR is equal to PV2 over MR. P1V1 over MR, P2V2 over MR. The MRs cancel, and we end up with P1 V1 is equal to P2 V2. So let me solve this for P2. I'm losing chalk here. Pressure at state 2 is equal to pressure at state 1 times V1 over V2. Now, let's see what we know here. I know pressure P1, I know V1, and I know V2. V1 is 4 times V2, 0.4 versus 0.1 cubic meters. So let's plug in. P1 is 100 kPa. V1 is 0.4 cubic meters, and P2 is 0.1 cubic meters. The cubic meters cancel out, and the units become kilopascals. And so this is 4, and I get 400 kPa. P2 is 400 kPa. P2 is 400 kPa. Okay? So P1, 100 kPa. So we have an isothermal compression process. As you squeeze the gas, the pressure goes up and the volume goes down. We start off at 0.4 cubic meters, and then we end up at V2, which is 0.1 cubic meters. But the pressure goes up to P2 is 400 kPa. So this is state 2. So the isothermal compression process looks like that on the PV diagram, up and to the left. It's not a straight line, it'll have a curve to it. So don't make it quite straight. Have a little arc to it. Convex, got a bit of convexity to it. Okay, so that's P2. That's P2. What else are we supposed to find? What else are we supposed to find? We're supposed to find the work from state 1 to state 2 and then to state 3. So find the total work. Find the total work. Well, how do we do that? Work 1 to 2 to 3. Oh, maybe we should finish the PV diagram before we go on to the work. Once we get to state 2, it says that we have isophoric compression to a temperature 1/2 of T2. So we have some sort of a cooling process going on, okay? Now, as you cool it, the pressure is going to fall. Fine. Pressure is going to fall. So the path from state 2 to state 3 is going to look something like this. Isochoric process, state 2 to state 3. Okay, I don't know what the pressure at state 3 is. I'm not asked for it, but that's basically what the process looks like, okay? Of course, the work is the entire area under the curve. So the boundary work from 1 to 2 to 3 is given by the area under the curve, all right? This is not a straight line here, so you cannot estimate the area under the curve using some sort of geometry, all right? We have to calculate the boundary work over the process. Okay, so what is the work from state 1 to state 2 and then to state 3? Well, that's equal to the sum of two works. It's the work from 1 to 2 plus the work from 2 to 3. It's a two-part process, 1 to 2, 2 to 3. Two-part process. So we got to calculate both works, okay? Let's do the hard one first. Let's calculate work from 1 to 2. Let's do that. Let's calculate work from 1 to 2. Let's see here. Work 1 to 2, and this is actually boundary work. What I mean by that is boundary work. That's going to be the integral of PdV from the initial volume V1 to the final volume V2, okay? Now, I need to get pressure as a function of volume somehow. What is pressure? Well, note that the ideal gas law is valid. PV is equal to MRT, okay? And that means pressure is equal to mass times the gas constant R times T divided by the volume. P equals MRT over V. All right? Now, I could substitute that into this integral here. The only little thing is, I know what temperature is. How do I know what temperature is over the process 1 to 2? It's an isothermal process, and I get temperature of 80 degrees C over here. So here's temperature T1, just convert that in Kelvin, and I could immediately plug it into the ideal gas law. So I do know the temperature. The gas constant, I could get it. I could get the gas constant if I wanted, fine. But I don't know the mass. I could calculate it. I could calculate the mass. I could. I know pressure, temperature, and volume at state 1. So I could use the ideal gas law to crank out the mass. I could do that. But I'll tell you what, I'm being a little bit lazy about that. I'm being a little bit lazy. I don't want to calculate MR. The MR term, I'm not interested. No, I don't want to calculate MRT. I don't want to calculate the MRT. So what I'm going to do is the following. I'm going to take advantage of the fact that this is an isothermal process. That means that this quantity here, this guy is a constant because it is isothermal. That whole term is a constant. That means pressure times volume is a constant. So this guy here is equal to a constant, and guess what that constant is equal to? The pressure times the volume anywhere along the path 1 to 2. I'm going to evaluate pressure times volume at state 1. I'm going to evaluate that at state 1, and that's equal to MRT. So I'm going to substitute P1 V1 into MRT. Because it's an isothermal process, MRT is constant. What is MRT actually equal to? It's equal to pressure times volume anywhere along the path 1 to 2. I do know pressure and volume at state 1. That's on the path. I know pressure and volume at state 1. I'm going to use what I know and a little bit of algebra instead of cranking out the mass. I don't need the mass. So this is going to give me pressure is equal to P1 V1, and then I have 1 over volume. Okay, so that's pressure from state 1 to state 2 along the path. Okay, let me make the substitution here then. Integral P1 V1 over volume, d volume, and that goes from V1 to V2. P1 and V1 are constant, so I can pull them out of the integral. And I get P1 V1 integral dV over V. And again, that's from V1 to V2. P1, V1 are constant. P1, V1 are constant, so I can pull them out of the integral. All right. Now, what's the antiderivative of 1 over V? It's a natural log of V, so I can immediately evaluate this integral. So I get P1 V1 natural log, and I have V2 over V1. P1 V1 natural log V2 over V1. I know everything. I know these volumes, and I know pressure P1. Let's see here. The pressure was 100 kPa at state 1. The volume was 0.4. So I have 100 kPa, 0.4 cubic meters, and then I got the natural log of V2 over V1. V2 was 0.1 cubic meters, and V1 was 0.4 cubic meters. The cubic meters cancels out in the natural log. It better be dimensionless in there. Okay? Let's see, what's my work? What is my work here? By the way, this natural log is going to end up being negative 0.1 over 0.4, so it's going to be negative, and I get negative 55.45. Now, what's my unit there? Negative 55.45. What is my unit? Well, I've got a kilopascal and a cubic meter. kPa, cubic meter. I'm starting to run out of space here. Tell you what, I'm going to go right over here. So I have negative 55.45 kilopascal cubic meter. Well, a pascal is a Newton per meter squared. The meter squared partially cancels out with the meter cubed, leaving 1 meter over, and I get Newton times a meter, which is a joule. So this is equal to negative 55.45 kilojoules. Work boundary. Work done by the system. Boundary work done by the system is negative 55.45 kilojoules. Box it up. Now, what does this negative sign mean? What does this negative sign mean? That means instead of the system doing work, work is being done on the system. Well, that makes sense. We're actually squeezing the system down. We're having to apply a force. We're having to apply a force at the top of the piston and push it down. So we're actually doing work. We're adding energy to the system in the form of work. That's what the negative sign is for. Note, W bound greater than 0, system does work. W bound less than 0, i.e. negative, work done on system. System does work, or work done by the system. System does work, work done on the system for when boundary work is negative. Okay? So I'm going to squeeze it down, and the work from state 1 to state 2 is 55.45 kilojoules on the system. That's what the negative sign is for. Okay? And we did that by actually evaluating the interval. Work is the integral of PdV. Okay? Now let's calculate the work for process 2 to 3. Work process 2 to 3. Work 2 to 3. Let's write the integral. It's equal to the pressure times dV from V2 to V3. Okay? Now, one thing to notice about the process 2 to 3, it's constant volume. It is isochoric. If volume doesn't change, then there's no area under the curve, and this integral is 0. 0. Why? Because it is isochoric. In other words, volume is constant. Volume is constant. Isochoric. No work from state 1, from state 2 to state 3. Okay. Work 1 to 2 to 3 is equal to boundary work, is equal to boundary work from state 1 to state 2 plus boundary work from state 2 to state 3. We just found out that was 0. And we get negative 55.45 kilojoules. So boundary work 1 to 2 to 3 is negative 55.45 kilojoules. Negative 55.45 kilojoules. Box it up. All right? Okay, so we use the ideal gas law to calculate the boundary work from state 1 to state 2. I think we better make sure that the ideal gas law or ideal gas behavior is valid. If you look over here, it's one of our assumptions, IGB valid. Maybe we should check it. Maybe we should check it. Let's check that IGB is valid. Let's see here. First of all, let's check the reduced pressure. Let's check the reduced pressure. Remember, for the ideal gas law to be valid, so let's see here. IGB, ideal gas behavior, valid if P reduced is less than 0.2 and T reduced is greater than 2, okay? You're safe. Z is approximately equal to 1, and your answers are going to be good to within 1% or 2 if these are the case. Let's find the maximum reduced pressure. Let's find the maximum P reduced maximum in our process. Let's find the maximum reduced pressure. And if it is below 0.2, we're good to go everywhere. Okay, let's find the maximum reduced pressure. Let's see here. Where might the max reduced pressure be? State 1 to 2, and then we get cooling. As you cool the gas, the pressure should fall, done isochorically. So a gas in a rigid container, you cool it, the pressure should fall. The maximum pressure should be at state 2. Maximum pressure should be at state 2. So that's going to be equal to P2 over P crit. P2 over the critical pressure. What is P2 over the critical pressure? Let's whoops. Sorry, give me a second. We need the critical pressure. We got the pressure at state 2, but we don't have the critical pressure. So let's go to the text here. And let's find the critical temperature and pressure for air. Oops. So table B1, air equivalent. It's a mixture of nitrogen and oxygen primarily. Molecular weight, critical temperature and critical pressure, 37.7 bar. P2, 37.7 bar. P2 is 100 kPa. And P crit was 37 bar. By the way, there's 1 bar per 100 kPa. So that cancels out. And I get 1 over 37. Bars cancel out. Oh, 1 over 37, what's that? Pretty small. Where's my calculator? 1 divided by 37. 0.02. 0.02. So P reduced max is equal to 0.02, which is definitely less than 0.2. Put a check there. First check on the validity of ideal gas over our process. Looks good. Let's calculate the minimum reduced temperature. Remember, T reduced has to be above 2. So let's calculate the minimum T reduced minimum. Reduced temperature minimum. That's going to be, well, temperatures here. Temperature T1 is 80 degrees C. Then we have isothermal compression. So T2 is equal to T1, which is 80 degrees C. How do I know that? Because it is isothermal compression from state 1 to state 2. Okay, so T1 is equal to T2. And then I know that T3 is a cooling process where T3 is equal to T2 over 2. All right? So temperature falls by 50%. By 50%. I'm going to interpret that as a 50% drop in centigrade. I think that's how I'm going to interpret it. So 40 degrees C. I think that's how I'm going to interpret that in centigrade, okay? In centigrade. Well, let's see. We'll see in a minute. Maybe both will work. I don't know. Let's see here. So T3, the minimum temperature in the process is therefore T3. So that's T3 over T crit. Let's see here, T3 is 273 plus 40 degrees C, and that gives me degrees in Kelvin. The critical temperature, what was that, 133 degrees Kelvin for air? We'll see. Air, 133 degrees Kelvin. 133 degrees Kelvin. Kelvins cancel. 273 plus 40. So we have 313 divided by 133, and I get 2.3. 2.35. T reduced min equals 2.35, which is greater than 2. IGB is valid. If I interpret T3 as half of T2 and I interpret that in absolute instead of centigrade, so what? I get 273 plus 80. 273 plus 80, what, 353, divided by 2, 176. 176 divided by 1.33 is not greater than 2. So I'm going to interpret this as T3 is half of T2 when I'm measuring it in centigrade. Okay, that's how I'm going to interpret it. In any event, reduced temperature and pressure criteria are met, and the ideal gas law is valid. All right, ladies and gentlemen, we will finish our discussion of work next time. We'll talk a little bit about other forms of work, and then we'll move on to a second path function called heat. Heat is a non-mechanical transfer of energy, and it's treated just like work. It's a path function. So we'll talk about heat and what we can do with heat. Take care, ladies and gentlemen.